Hello everyone, I'm Bhavna Chandrasekhar, a software development manager at Amazon. I'm here to talk about how Amazon builds AI-enabled perception for robots. I lead a team of applied scientists and machine learning engineers working to advance fulfillment at Amazon. We're solving some exciting problems, and we'll talk about one of them today. If you've wondered about how Amazon is thinking about AI-enabled robots, today we're going to cover one of the robots called Robin, explore difficult AI problems that exist in the robotic manipulation space, and how Amazon Robotics approaches solutions to them. I'd like for us to have two key takeaways from this session: how to build and bring perception systems for robots from prototype to production, and two, what are the challenges of scaling a vision system for high accuracy performance. So we'll go over some of the robots that we build at Amazon. We'll talk about robotic manipulation. We'll do a case study on Robin, a package manipulation robot, and also talk about how we scaled robotic Robin perception. So let's get started. Amazon works on a variety of robotic problems. They span across a wide variety of applications, from moving items in warehouses, for example with our Canvas carts or our AR drives, as well as robotics manipulation projects, to improving safety of our associates and customers, as well as improving delivery experience to deliver to our customers, for example with Scout and Primary robots. We're specifically going to talk about robots that operate in warehouses today. Here's a couple of videos of our robots that are in warehouses. The group that I work for, Robotics AI, works on both two broad categories of robots: robotic manipulation as well as autonomous mobility. There are several commonalities when we think about these two categories of robots. Both have perception systems, planning systems, control systems. Perception systems help you perceive what kind of environment you're operating in, what items you're manipulating. Your planning stack will help you understand what is the navigation that you need, how do you actually move your item, and the control stack essentially helps you achieve those movements. Within these broad categories, there are several key differences that exist between autonomous manipulation and autonomous mobility. One of the key differences that stands out is really safety systems. In autonomous mobility, you have greater emphasis on safety systems because they're widely interacting with humans, potentially interacting with humans. With manipulation robots, they can be confined, they're on fixed ground, don't need to move a lot. In this talk specifically, we're going to focus on robotic manipulation problems. Let's go to our next slide. Okay. Okay, so we're manipulating items in warehouses. Here you can see three images of robots that we've worked on or building that are talking about how we manipulate packages. So the first one, you can see packages that are coming off of conveyors, and we're picking them and placing them onto drive units. Second one is an example of a robot that is trying to manipulate items into racks. And then the third one is you have items within a bin or a tote, and we're trying to pick up those items. So what do these items or packages actually look like at Amazon? There's a broad category of classes of packages themselves. You have brown boxes, you have yellow jiffies, you have white poly mailers. You have them in rigid or deformable nature. So like as you pick them up, they might change shape, they might move, the center of mass varies. And they also come in a variety of different types of packaging that are not inherent to these 3 or 4 categories that I just described. For example, we are continuously improving our frustration-free packaging experience, and so sometimes we might have packages that are shipped in their own container. For example, blenders or juicers or coffee makers, for example, that are not wrapped in another Amazon packaging and are shipped with certain kinds of brand labels and information. What do items look like at Amazon? We can broadly classify them or categorize them into 4 categories. Rectangular, more or less in cuboidal shapes, for example, toys or remotes or things that are in rectangular or cuboidal packaging. Compressibles, so things that if you apply pressure can change shape. Toys, clothes is an example. You might have a cable, for example, like as shown in this image here, that can change shape, can be compressed. Things that are in bags. Several of our items in warehouses actually come pre-bagged, so we're able to pick them differently than how we would pick, for example, a box. And everything that doesn't fit in this category, imagine as an irregular shaped object. For example, the Swiss knife or like weirdly shaped wrenches and so on. Each of these categories actually have their own version of challenges that they pose to robotic manipulation, and we'll cover those in a bit. One of the biggest challenges in building robotic manipulation projects at Amazon is the scale, right? We see a lot of novel packages and items, and being able to manipulate all of these items, sometimes unseen for the first time, can be really challenging. Humans are really good at solving that problem. We can see a scene and understand exactly which item is what is the degree of occlusion that exists, and also like estimate the 3D shape, understand if it's going to change shape as you pick it up. But we want to build that intelligence into the robot itself, and that's a challenging thing to do. Computer vision algorithms are getting there, but there's still a long way to go when you think about millions of unique items at the Amazon scale. Another challenge that we have is actually being able to sense the items themselves. Humans, with one of our greatest sensing ability, our eyes and our touch, can understand and see things better than many sensors can. For example, when we have reflective surfaces, our depth sensors can have holes in them, or like they might not perceive them with high confidence. And being able to estimate 3D shapes, for example, can be really challenging. So quick recap so far: challenges that exist in robotic manipulation, adapting to novel packaging or items, sensing challenges, for example, with reflective surfaces. Let's go into our third category of challenge, which is manipulating deformables. For example, this T-shirt, which is in a bag, when we perceive it, it looks more or less rectangular. You go to pick it up with a robot arm, it's going to change shape because it's a deformable item. When you're dealing with deformables, you might actually want to understand inter-item relationship. For example, how much degree of occlusion it might be surrounded by, what the item itself is, in order to understand the characteristics of how it might deform. And that brings us to our next challenge, which is identifying the item in clutter. So this is a really hard problem when you take the range of unique items that go through Amazon. So you might have information of this is what an item looks like from our catalog, like when you see it on the .com website or when you see it singulated by itself. But identifying that in a clutter is actually quite challenging even for humans. And we want to be able to solve that problem in order to effectively manipulate it down the line. So quick recap on some of the challenges that we've talked about: novel packages, novel items that we see for the first time, sensing reflective surfaces, third one manipulating deformables or compressibles, identifying items in clutter when there's a large variety of them, and the last one is actually avoiding damage. Here you'll see an image of, with a couple of tiles missing at the bottom left corner. This is an okay item to manipulate, right? But we don't want to ship this to our customer because it's clearly missing a couple of tiles. But here's an example of a coffee bag that's probably torn open. A couple of grains of coffee, coffee beans have already come out. But manipulating this might actually mean that we would be increasing the spillage and essentially rendering this entire area unusable. So this is an example of where we might not want to even manipulate it. So detecting and avoiding damage is also a big challenge when it comes to robotic manipulation. Again, a quick recap of the challenges that we talked about: novel items that are being introduced, sensing challenges, being able to manipulate deformables and compressibles, being able to identify items in clutter when you have a large catalog, detecting and avoiding damage so you don't ship damaged goods to our customers. Cool. So far we talked about what are some of the broad categories of robots we build, what does robotic manipulation at Amazon look like. Now let's talk about Robin, which is a package manipulation robot that we put to production. Here you'll see Robin in action, and I'm going to let this video play out for a couple of seconds here. You can see it's moving packages from a cluttered conveyor onto carrier robots. A little bit of background about what Robin is. As I said, it's an autonomous manipulation robot that picks packages from clutter and places them onto these drive robots. And these drive robots then go and sort these packages via zip code or area code that are then sent to our delivery partners. We built the intelligence for this robot to perceive the packages, decide which package should be picked and how it should be picked and how it should be placed. So let's decompose the Robin problem into a little bit more granular level. So you have packages that are arriving on the conveyor. We have an instant segmentation model, which is part of the perception system, that we use to identify the packages. We have the robot, the yellow arm that you see, that picks up the packages and places it onto the carrier robot. Once it's placed onto the carrier robot, again another perception system, classifies the place scene, as we call it, as having only one package, so it can be then sorted effectively to its destination, or having a defect, meaning it doesn't have any packages at all, or maybe it has more than one package, which happens because robots aren't perfect. And then once that's done, the carrier robot then drives off. Today we're going to so before we dive into the challenge, today we're going to focus primarily on the two perception systems that I talked about. But first, what are some of the challenges in Robin? Very similar to what I discussed earlier with challenges in robotic manipulation, we have new and unseen packages. At Amazon, packages can come in a variety of materials, visuals, weights that make it challenging for not just perception to handle things, but also for planning as well as control, as well as the design of the end effector itself. Here you can see packages with minions, you can see packages that are being shipped on their own. We have packages with pop stars on them, Grinches, you name it. And they vary quite a lot between seasons, for example. The second challenge that I want to talk about is scaling in production. Here's a example of like what we thought clutter would look like when we started out in the lab setting on the left side, and really on the right side is what really comes in production. So being able to kind of adapt to the volatility of a warehouse in terms of different varieties of packaging, volumes of packaging, degree of clutter is an important challenge that we have to address in Robin. The third one is mitigating and avoiding damage. Here you see some packages that have crushed, that have been crushed from either the robot or upstream before it arrived to the robot itself. There can be holes or tears. There can be deconstruction. So like, the packaging tore open and now the item is outside. There can be spillage. So all of these are categories of damage that can exist. But sometimes damage can be quite subtle. For example, with this package, do we decide to ship this to our customer or do we not ship this? Largely depends on what the item is inside, and if that level of damage has essentially damaged the packaging so that it doesn't make it to the customer effectively. So quickly summarizing the challenges in Robin, there's a good overlap between challenges in Robin and challenges in robotic manipulation in general. Novel packaging, scaling in production, and adapting to the diversity, and mitigating and avoiding damage itself. Those are the broad streams. So we started with Robin package manipulation as one of the first applications that we want to learn from to deal with this smaller subset of challenges. But this is a stepping stone to longer term roadmap for manipulation at Amazon. Okay, let's talk about the two perception systems that I mentioned earlier, the instant segmentation model and the classification model. In the instant segmentation model, we're looking at essentially being able to adapt to a wide variety of packages. You want to handle deformables where it's hard to even say where one item starts and another one ends, or like one item ends and another one starts. Because of our climate pledge initiative, we're constantly investing and inventing in sustainable packaging options that increases the complexity of package types that we see. There's a variety of them. We're actively pursuing reducing the packaging material altogether, so we see more of the items themselves being shipped where possible. So those are challenges that like our instant segmentation model has to adapt to. Let's talk about the classification model, which is where we verify if there's more than one item that made it onto the carrier robot. There's several categories of errors that can come. We are interested in classifying if one shipment made it onto the robot and then effectively send it downstream. But there can be incorrect placement. There can be things that have broken out from the package. There can be lighting problems. There can be like multiple packages that have made it onto the carrier robot. So this becomes there seems to be a lot of different defects, let's say, that you can introduce that this model has to learn about. But the interesting thing is that these defects don't happen equally as the successes do. So there's a long tail mining problem where these occurrences happen very infrequently, but we still want to catch them because those are defects. So we're looking at training a high class imbalanced classification model. Okay, so now that we have two, or like we've talked about the perception systems, and both of these perception systems use ML models in them. Let's talk about how we scaled Robin perception. When I think it's no surprise when we're using ML models in production, the biggest challenge that we encounter is data. When we first started out building these ML models, we actually had few hundred images of what packages look like, and few hundred images of what defects look like. And typically, instant segmentation models or classification models use somewhere between hundreds of thousands of labels to millions of labels. So the way that we actually overcame this data problem was by using some of the bootstrap methods. One was fine-tuning on pre-trained models. So effectively, if there was already an instant segmentation model that was performing well, adding our domain data and really fine-tuning the last few layers helped us get a model out for production. We invested in synthetic data and used that to kind of mimic our defects that we were creating, or that we thought how defects could arrive, and also creating data augmentations, right? So we have a few hundreds images. How can we change that effectively to kind of trick the ML model into thinking that these are new samples that it should learn from? So let's talk about why we only had a few hundred samples. In order to train an instant segmentation model, you need instance labels. When you look at this image here, you can see kind of our SageMaker ground truth setup for how we annotate these instances. When it's a box or a fairly cuboidal object, you can draw the polygon with like 4 to 5 points, and that looks good. But whereas when it's a deformable, it can range anywhere between like 6 to 20 points because of how the shape forms itself. Because of this is a very time-consuming work, and so we looked at investing in synthetic data. Here's an example of what synthetic data gets us. We get bounding boxes, we get labels of what packages they are, we get package boundaries, and the data doesn't look too far from real world. Here's some more examples of synthetic data and real world data. I don't know if you can tell the difference between which side is synthetic and which side is real world data. The left side is actually synthetic data and the right side is real world. So we actually were able to more aggressively simulate higher number of packages in a scene, increase the clutter in the scene itself. So now that we use these techniques, got the first ML model out, or the nth ML model out, how does that adapt to diversity? How did we do in terms of rolling Robin out into many different facilities? Let me motivate this with these example images here. These are images of our carrier robots from different sites or stations. You can see there's a wide variety of lighting changes. The position of the camera is changed. The environment, like the peripherals of the drive itself is different. How did we do? How did the ML model do in its first attempt? I'll say not so well. And the way that we were able to scale for the wide variety of sites was by actually applying what we call continuous learning. Essentially, we want to be able to monitor when the model is not performing well and recover that performance by adding new data or retraining the model again. And we want to do that automatically, right? That's what lets us scale in production. So imagine you have an ML model that's deployed out to several robots or one robot. You are gathering data from that robot, and you're continuously analyzing that data for anomalies, for out of distributions, Has the model suddenly shifted what it's predicting? What are the high-level statistics around our predictions? And has the input distribution changed? Once you have that information, you then sample for, we want to investigate with ground truth. It might be annotators, it might be other ML models that you use to effectively check how your model that's deployed in the field is doing. Once you're able to monitor that, you then have a decision point of, do you want to update the model that's out in the field? If you do, then you retrain your model by curating a data set based on your old data, as well as new information that has shown you where the model is not performing as well as you had hoped. You retrain the model, you effectively check that performance compared to your previous model, and make a call on deploying it out into the field. This is a continuous learning loop that helps you continuously update and roll out effective ML models that can scale and generalize to the wide variety of changes that you might see. Here's an example of where the continuous learning loop actually was really effective for us. In the first image, that's from October 2021, you see the model, the instance segmentation model that we had in Robin is missing some of the black packages, and it also doesn't catch as many occluded packages, meaning things that are behind other packages. As time goes on, we've seen a few black packages come through. The model has been retrained automatically. In November, you start to see that the model is able to now pick up on the black packaging. It's able to classify or like identify, segment those packages. By February of 2022, you're actually seeing that it is now way more effective in even detecting and finding occluded segments. So meaning, that yellow mailer that's behind another brown mailer is now effectively segmented, and you have a better performing model overall. In conclusion, I've been able to kind of walk through what Robin is, how Robin scaled in production, or like how the Robin model scaled in production. Here's Robin in action. Today we have hundreds of Robin stations out in the field, sorting millions of packages a day. This year, our plan is to go to and expand to thousands of Robin stations, and we're excited to see how our ML models scale. Here are also some resources about the work that we've done on Robin that are available for read. With that, I'd like to wrap up my talk, and thank you so much.